Kia ora Year 11 and 12. This video is going to look at how we can choose which function to use to model a curve. And there's not one right answer here. I'm giving you 2 points, and I want you to see that there are several different options that are going to fit that curve quite well. So the curve I'm working with is this one here. Now, the eagle-eyed among you may actually figure out exactly what this curve is. I'm going to get to that, but if you're doing that, just park that idea now or scribble it down on a piece of paper. What we're going to try and do is to take different functions in their general form and fit the information that we've got into this. So I'm going to start by saying, what are the 2 points that I've got? Well, I've got point F here, sorry, point C here, and point D here. Right, so C is 1, 6, and D is 3, 2. Okay, so if you think about the families of curves that we've looked at, there are quite a few that might fit here. Hopefully here, the first one that you might look at, which is quite nice and easy, is a hyperbola, right? So choice 1 is a hyperbola. And then choice 2, there are a few other curvy ones that we've looked at. I'm going to focus on the square root graph. And lastly, I'm going to focus on the exponential. And the maths of trying to figure out the A, B, and C factors is a little bit different for each one, but it comes down to the same idea. For each of these, I'm going to write the most general form of the equation. So for the hyperbola, we know that we can have y equals A over x plus B plus C. Now this plus C is going to be, the plus C is going to be where I've got a vertical shift, so I'm going to have an asymptote at that value. The plus B in here is giving me my vertical asymptote at negative B. Right, so let's draw some axes up quickly. So the B here means a vertical asymptote there, and the C here means a horizontal asymptote here. Don't think too hard about the A. I mean, the A is a vertical stretch factor. But what we're going to have to do is we're going to have to guess one of these because we've only got 2 points. And if we've got 2 points, 1, 2, then we can figure out a curve that fits with 2 of these, but we can't figure out all 3. So we're going to have to make an assumption about one of them. So that's what the hyperbola is going to look like. Now, I think we might as well do that one first. So looking here at the curve, I've only got part of the curve drawn, but there's nothing stopping me taking my pencil and just extending that out and seeing if am I confident about where that's going to have an asymptote. Well, I think I am. I think I'm happy to assume that it's going to be 0, or maybe it's going to be close to 0, but let's just assume that it's going to be 0. So that means that I'm going to say, let's assume that C is 0 and there's an asymptote on the x-axis. The other thing I could do is I could take the curve up this direction, and I could guess that I think that there's going to be a vertical asymptote that's on the y-axis. But I only need to do one of those assumptions because I've got 2 points, so I can solve for 2 things. So let's just write some of that down. So assume C equals 0, which means that, what am I trying to say? The horizontal asymptote is at y equals 0. So what does that mean I'm left with? Well, I've got y is equal to A over x plus B. And I've got 2 points, 1, 6, and what's the other one? 3, 2. What do I have to do now? Well, I substitute in those 2 points and I solve for A and B. Remember that I'm substituting for the y and the x, not the A and B. So off we go. We've got 6 is equal to A over 1 plus B. And I've got 2 is equal to A over 3 plus B. I'm going to get 2 linear equations and I'm going to chuck them into my calculator. Yeah, I bet you can't believe I said that, but I did. But in the video, I'm going to do them by hand to make sure that you remember. So I've got 6 plus 6b is equal to A, and 6 plus 2b is equal to A. So just from looking at those, what can we see? Well, we can see I've got 6 plus 6b is equal to 6 plus 2b, which means that 4b is equal to 0, so b must equal 0. So that was pretty easy with no calculator. But I want to show you how to rearrange it so that it will go into your calculator. So there are my two equations. The calculator needs it in this form. Something x plus something y is equal to a constant. So this first one, we'll do this. A, so it's 1a minus 6b is equal to 6. And the next one is 1a minus 2b is equal to 6. So in your calculator, what you're going to put in is 1, negative 6, and 6, and 1, negative 2, and 6. And I think where you do that is under equa, and then simultaneous, and then degree 2. Okay, so what's that told me? Well, it's told me that b is equal to 0. So now I need to find a. And I've got 6 plus 6b is equal to a. So 6 plus 0 is equal to a. A equals 6. So let's now go back to my general form, and I've got y equals a over x plus b plus c. And I guessed that this was 0. So now I've got y equals 6 over x. Now, that is exactly what I put into GeoGebra when I made that graph. Let's go back and have a wee look at the first page. So just looking here, that's exactly the right graph. And you could have seen that if you'd noticed at that point there was 2, 3, you could have got it from there as well. But suppose that I hadn't gone with a hyperbola first. The next one I'm going to look at is actually kind of cool, and that's a square root. So let's get rid of some of this, because we need to think about the best way, the smartest way to model a square root graph here. So let's think about the basic form of a square root graph. Well, we start with our axes like this, and this is the graph of y equals root x. This graph here is more like what we want. This is y equals negative root x. So we've got something here which looks kind of steeper through here, and it's got a starting point at 1, 6. So it's been shifted out 1 and then up 6 to here. Right, so the form of the square root that I'm going to use to model will look like this. I will use y equals a times root x minus 1, because it's been shifted out, plus 6. So I've now used this point to form this equation. I've got one point left, which is the point 32. And I'm going to substitute that in to get a value for a. All right, so let's do that. I'm going to do that on a separate page. So y is equal to a root x minus 1 plus 6. 3, 2 is on the curve. So I can write this. 2 is equal to a root 3 minus 2 plus 6, giving me negative 4 is equal to a times root, sorry, that should be a 1 in there, not a 2, a times root 2. What do I get now? Well, we're going to chuck that into our calculator. Negative 4 over root 2 is equal to a. A is equal to negative 2.8284. So there we go. Right, so that wasn't bad at all, right? Because I had the functional form that had the starting point matching up to one of those points. So let's go back to that. We've got this point here at 1, 6, and we're going whoosh like this. And we're going to see how well a square root function fits. So this point here was 3, 2. So in the hyperbola case, we were solving for a and b. Here, we made an assumption. Well, we said that it went through here, and we've only got one thing to solve for, which is a. So we've found a now, and it makes sense that it's a negative value because it's upside down. So that gives me y is equal to negative 2.8284 root x minus 1 plus 6. So that would be the function that I used to model that bit of the curve if I'd used a square root function. So now the moment that you've been waiting for, which is how good is it? So let's have a look. It's really pretty good, right? The brown curve in here is the actual curve, and the green curve is our square root curve, which is y equals negative 2.82884 root x minus 1 plus 6. So again, just look at what I did. I've got a shift out of 1 unit, and I've got a shift up of 6 units. Okay, so that's where that's coming from and where that's coming from. And then all I'm doing now is figuring out if it's like this or like this or like this. In other words, I'm doing the vertical stretch factor. So that's the square root one done. Now let's go back to the start and think about our third possibility. Well, we've done the hyperbola and we've done the square root, but we could also model this with an exponential. Now I'm going to start this in this video, but I'm probably going to run out of time. But I really want to do it because when I look at that, I see that it kind of does look sort of exponential. So we might try that. Right? So my basic exponential goes like this. So this might be y equals b to the x. That's where b is greater than 1. But where I've got b less than 1, I'll get this, y equals b to the x with b between 0 and 1. So you can see that if I'm looking at this bit of the curve here, it kind of looks like this, right? So how could I write the general form for the exponential? Well, let's have a look. I need to pin some things down. I've got 2 points, and my most general form is this, y equals some base b to the power of x plus c plus d, right? So this is my vertical shift, this is my horizontal shift, and this is my base. So again, I've only got 2 points, and here I've got b, c, and d. So I can't work this out unless I make an assumption. So what I have to do is take that highlighter, and we're going to see where do we think there's an asymptote roughly in here. And we can be reasonably rough with this. So take your highlighter or your pen and just put it through like that, and it looks like it's at about 1. Okay, so we're going to assume that there's a horizontal asymptote at 1. So we're going to work with this and make d1. So y equals b to the x plus c plus 1, assuming horizontal asymptote at y equals 1. Right, so now all we have to do is to substitute things in. I've got 1, 6, and I've got 3, 2. So 6 is equal to b to the power of 1 plus c plus 1. That gives me 5 is equal to b to the power of 1 plus c. The next point gives me this. 2 is equal to b to the power of 3 plus c plus 1. So 1 is equal to b to the power of 3 plus c. Now your graphics calculator won't help you here, which is why modelling an exponential is a little bit harder than some of those other ones that we've done. What do I do? Well, if I've got this is equation 1 and this is equation 2, I'm going to go like this. It doesn't matter which way around, but I'll do 2 divided by 1. So b to the 3 plus c over b to the 1 plus c is equal to 1/5. Now here I've got the same base, so I subtract the powers. And I've got b to the power of 3 plus c minus 1 plus c is equal to 0.2. Right, I'm using decimal because it's not recurring. Here I've got b squared is equal to 0.2. So b is equal to root 0.2, which is roughly 0.447. So we're getting closer now. We know that y is equal to 0.447 to the power of x plus c plus 1. I just have to solve for c. Right, so this is the last little bit in 10 seconds that I can't quite do. I'm going to do this in part 2 of this now. Thanks for watching, and I'll be back soon.